Hi everyone, myself Dr. P. Ashok Babu. So in this video, I'm going to discuss about the Ampere Circuit Law and applications. So first of all, we'll discuss the what is Ampere Circuit Law. So here Ampere's Circuit Law states that the line integral of H, the line integral of magnetic field intensity H around a closed path is same as the net current enclosed by the closed path. So I repeat once again, Ampere's Circuit Law states that the line integral of a magnetic field intensity H around a closed path is the same as the net current I enclosed by the path. So in other words, we can express it as, so it is a closed integral H into dl is equal to current enclosed in the closed path. So Ampere's law is similar to the Gauss law, because in Gauss law, so we'll discuss about the magnetic flux density, electric flux density D and some flux. So here we'll discuss about the magnetic field intensity and current. So here Ampere's law is similar to the Gauss law, since Ampere's law is easily applied to the easily applied to determine magnetic field intensity when the current distribution is symmetrical. So whereas in electric field, the charge distribution is symmetrical. When there is some charge distribution is symmetrical, we can apply the Gauss law. Coming to the Ampere circuit law, if the current distribution is symmetrical, then only we can apply the Ampere circuit law. It is a difference between electric field and magnetic fields. So here, let us assume the equation 1. If you apply Stokes theorem to the left-hand side of the equation 1, if you apply Stokes theorem to the left-hand side of the equation 1, so here the equation 1 is, it is a line integral. So if you apply Stokes theorem to the line integral, Stokes theorem will convert to the line integral to a surface integral. Therefore, here I enclosed equal to the line integral of H into dl will becomes the surface integral del cross H into ds. So here already we know that the current enclosed equal to, so it is the integral of surface integral of J into ds. We know that the current enclosed I is equal to surface integral J into ds. So here if you compare the equation 2 and 3, if we compare the equations 2 and 3, we can write del cross H is equal to, del cross H is equal to J. Del cross H equal to J, which is the Maxwell's third equation, or the Maxwell first equation for magnetic field. Maxwell third equation, or we can call it as a Maxwell's first equation for magnetic field. So it is essentially Ampere's law is, or we can call it as a Ampere's law in differential form, because it includes a differentiation del cross H equal to J. We can call the Maxwell equation or Ampere's circuit law in differential form or point form. Now we'll discuss about some of the applications of Ampere's circuit law. So same as the Gauss law, we need to follow some rules and regulation when we are applying the Ampere's circuit law to any field. So here the rules and regulations are, first one is we need to check that whether there is some uniform current distribution is there or not. First one is we need to check that uniform current distribution is there or not. So if there is some uniform current distribution, then only we can apply the Ampere circuit law to a particular line integral, line or a surface or volume integrals. So here second one is, let us assume there is some uniform current distribution. When there is uniform current distribution, second one, we need to construct Amperian path. We need to construct a Amperian path. So after constructing the Amperian path, we can apply the Ampere circuit law to a particular surface. So here let us assume first application is, it is infinite line current. For infinite line current, you let us assume a line integral, let us assume a point charge, let us assume a point magnetic field, so which is placed along the z-axis, or consider an infinitely long filamentary current I along the z-axis. So here to determine the magnetic field intensity at a point P, we need to apply the Ampere circuit law. To apply Ampere circuit law, here we need to check that three different conditions. So first of all, we need to check that, so whether there is some uniform current distribution is there or not. So because the point is located at, the magnetic field is located at origin, we can assume that there is some uniform current distribution. If uniform current distribution, then we need to construct Amperian path. So construct an Amperian path like this. So it is a Amperian path. So for this Amperian path, we need to apply the Ampere's circuit law. So here this path on which the Ampere's law is to be applied is known as the Amperian path. So this particular path is known as the Amperian path. So according to the Amperes circuit law, we know that the current enclosed is equal to the magnetic field intensity. So here I is equal to, we know that H phi into A phi. H phi into A phi. So here we can write, because it is a line integral, here in place of this we can write the dl. Actually it is, if you apply Amperes circuit law to that particular circle, Amperian circle, according to Amperes circuit law, the current enclosed is equal to, it is integral, line integral of H phi into A phi into dl. So because the total, it is a Amperian path is a circle, since it is a circle along the phi direction. So in place of dl, we can write rho d phi into A phi, because it is a circle. In place of dl, we can write rho into d phi into A right. Therefore, it is in place of dl, here I am writing rho into d phi into A phi. So where A phi is a unit vector along the phi direction. So here H phi is constant, we can keep outside. H phi into integral rho into d phi, because rho is also a constant, we can keep outside we can integral. Therefore, it is H phi into rho integral 0 to 2 pi, because the phi extends from 0 to 2 pi. The phi limits are 0 to 2 pi, and theta limits are from 0 to pi only. So because phi extends from 0 to 2 pi, the limits for integration are 0 to 2 pi, 1 into d phi. So here if you integrate that, it is between the limits 0 to 2 pi, it is phi, between the limits 2 pi to 0, therefore it is 2 pi. The value is 2 pi. Therefore it is, we can write H phi into 2 pi rho. Therefore we can find out the H value. H is equal to, it is actually the current I is equal to H phi into 2 pi rho. Therefore, where H phi is the magnetic field intensity, rho is the radius of Amperian path. Therefore, we can find out the magnetic field intensity H is equal to I by 2 pi rho into A phi, where A phi is the unit vector along the phi direction. This is about the application of Amperes circuit law to some infinite line current, Now we'll see the second application. So it is infinite sheet of current. So to find out to apply Amperes circuit law to a infinite sheet current, let us assume some infinite sheet, so which is located along the rectangular coordinate system. So consider an infinite current sheet in the z equal to 0 plane. So here, if the sheet has a uniform current density, let us assume the sheet is having some uniform current density, some k. So k is equal to ky into ay. So which is, the sheet is having the uniform current density, k is equal to ky into ay amperes per meter. Now we need to apply the Amperes circuit law to some infinite sheet current. So to apply that, we need to check that. First one is whether there is some uniform current distribution is there or not. So because of it is infinite sheet, so automatically we can assume that it is having some uniform current distribution. So when there is some uniform current distribution, we need to construct an Amperian path. So let us assume the Amperian path is, so it is an Amperian path. So it is a rectangular box is Amperian path. Let us assume it is an Amperian path which is having the sides 1, 2, 3, 4, and the sides are, one side is B and other side is A. It is just like a rectangle. So rectangle is having the sides B and A, and it is 1, 2, 3, 4 like that. So the current will flow 1 to 2, 2 to 3, 3 to 4, 4 to 5 like that. So here like that you assume some Amperian path. Here we need to apply because it is having the uniform current distribution, we need to apply the Amperes circuit law. So when we are applying Amperes circuit law, one more thing here, we need to check that here it is having the current distribution. The sheet is having the current density of k into ky into ay. So here we are applying the current density along the y direction only. Let us assume it is y direction. So along y direction we are applying some current density. So along the y direction we are applying current density. Along the y direction only we need to consider the total current distribution. So in remaining y and z, in remaining x and z directions, we have current density 0. Along x, z directions, the current is 0. Like that we need to assume, because the total current density is along the y direction. Along y direction only we need to consider the current value. Along x and z directions, the current intensity 0. So according to Amperes Circuit Law, if you apply Amperes Circuit Law, the current enclosed I is equal to, it is a closed integral h into dl. Closed integral h into dl. So which is having the some current intensity, let us assume ky into b. Ky into b, which is having the current density ky into b. Now, here I am defining the magnetic field for positive and negative axis. So let us assume the magnetic field H is equal to H naught into AX. H naught into AX if Z is greater than 0 for positive quadrant. The magnetic field intensity for negative quadrant is H is equal to, let us assume, minus H naught into AX for Z less than 0. So like that you define the magnetic field intensity for positive quadrant and negative quadrants. Next, apply Amperes Circuit Law. Here if you apply Amperes Circuit Law, so it is a line integral h into dl. Line integral h into dl. So here because we assume a rectangular box, which is having the sides 1, 2, 3, 4, sides b and a. So we need to consider each and every side to integrate the total, or to integrate that, or to find out the total magnetic field intensity. So therefore, the total rectangular is divided into 4 parts. Integral 1 into 2 plus integral 2 to 3 plus integral 3 to 4 plus integral 4 to 1 into h into dl. So here we need to find out the each and every integral, then we need to substitute into equation. Therefore, h into dl is equal to, here the first one is 0 into minus a. So here there are different directions. So let us assume the current flow 1 to 2, 2 to 3, 3 to 4, 4 to 1. If I assume the current direction from 1 to 2 is positive, we need to assume that 3 to 4 as negative. And if you assume the current direction from 2 to 3 positive and 4 to 1 is negative, like that we need to assume that because the both sides are opposite to each other, we need to assume that one as positive and another one as a negative. So here the first one is, so because it is along the, it is y direction, along y direction only we have the magnetic field intensity. Along the y direction only we have the current, because the current flow we have the magnetic field intensity along the y direction. In z direction it is along the z direction. In z direction the magnetic field intensity is 0. So along 1, 2 direction, so the side is a minus a, I have assumed as a negative sign. Therefore 0 magnetic field into minus a plus next one is again assume that 2 to 3 is negative. If I assume 2 to 3 negative, 4 to 1 is a positive. Therefore, it is minus h naught into, it is minus b, because I assumed it is a negative axis. So it is minus h naught into minus b plus along 3 to 4, because 3 to 4 is along z direction. So it is also 0 plus h naught into beta, h naught into b. So because along it is a positive, 4 to 1 is a positive, you assume it is h naught into b directly. Therefore, these two terms cancel each other because it is 0, 0. So therefore, we have h naught into b plus h naught into b. The total value is 2 h naught b. Equate the equations 1 and 3. If we equate the equations 1 and 3, in one we have current enclosed equal to ky into b. So here we have the magnetic field is equal to 2 h naught b. Therefore, if we equate the two equations, ky into b is equal to 2 h naught b. So b cancel each other. Therefore, the magnetic field h naught equal to the magnetic field intensity h naught equal to half into ky. So here, if we substitute this equation 4, if we substitute equation 4 in equation 2, we can find out the magnetic field intensity for positive quadrant as well as the negative quadrant. So here, therefore, if we substitute the equation 2 in equation 4, the magnetic field intensity for positive quadrant is, it is half ky into ax, half ky into ax. So it is for where z is greater than 0. This is for positive quadrant, and the magnetic field intensity h is equal to minus half into ky into ax, where z less than 0. This is for negative quadrant. So like that we can define for positive and negative quadrants the magnetic field intensity for positive and negative quadrants. So in general, so we can define for an infinite sheet which is having the current density k. Then we can define the magnetic field intensity as h is equal to half ky into an, where an is the unit vector, along that infinite sheet of current. So this is the expression for magnetic field intensity of an infinite sheet in general case. So this is about the second application. Third application is we need to consider an infinite long coaxial transmission line. Application of magnetic field in Amperes circuit law to infinitely long coaxial transmission line. To apply that, here let us consider an infinitely long transmission line consisting of two concentric cylinders having their axis along the z-axis. So here for infinitely coaxial transmission line, because it is a coaxial, it is having the two circles. So the first circle, the inner circle and outer circle. The inner conductor has a radius of A. Let us assume an inner conductor is having the radius A and carries a current I. Inner circle carries a current I, while the outer conductor has the inner radius B. So here from figure we can observe that. So it is the outer circle. So here outer circle is having the radius B and which is having the thickness T, and carries a return current minus I. So here you please observe the two circles. The first one is the inner conductor is having a radius A and carries a current I. So whereas the outer conductor is having the radius B and which is having the thickness T, and which carries a current of minus I. So like that, assume two conductors, inner conductor and outer conductor. So assume before applying the Amperes circuit law, we need to check that whether there is some uniform current distribution is there or not. So let us assume because of it is a circle, a uniform charge distribution is there. So when there is some uniform charge distribution, we can apply. We need to construct a Amperian paths. So here because of two conductors, we need to construct different Amperian paths. So here we can construct the Amperian paths of 4 Amperian paths. So it is the inner circle 1, 2, 3, 4. So here from figure we can observe that there are 4 Amperian paths. We can construct 4 Amperian paths by using the figure. So here first one is which is having the it is an inner circle which is having the radius A. Therefore the Amperian path can be constructed as 0 less than or equal to rho less than or equal to A. So which is a radius of first one, which is a limits of the first Amperian path. Let us assume second Amperian path. So here second Amperian path, so which is having the radius greater than A and less than B. Therefore A less than or equal to rho less than or equal to B, where rho is the radius of Amperian path. Next third one. So here if you assume a radius of that outer conductor is B, and we can assume the thickness, we can construct other Amperian path. Therefore the third one is the limits of the third Amperian circuits are B less than or equal to rho less than or equal to B plus T. And fourth one is completely outside the conductor. Therefore it is rho greater than or equal to B plus T. So like that we need to construct Amperian paths, 4 Amperian paths. We need to apply Amperes circuit law to the 4 conditions. So we'll see one by one. First one is for the first region, it is 0 less than or equal to rho less than or equal to A. 0 less than or equal to rho less than or equal to A. So apply Amperes circuit law to path 1. So here if you apply Amperes circuit law to path 1, so it is a line integral H into dl is equal to a current enclosed. So we can calculate we know that the current enclosed is equal to, it is surface integral J into ds. So first we will find out the surface integral J into ds, then we will substitute into the derivation. So here since the current is uniformly distributed over a cross section, so we can find out the current density I is equal to, the current I is equal to, it is a surface integral J into ds, where J is common, keep outside. Therefore surface integral 1 into ds. So here the surface area of a circle is pi r square, where r is the radius of a circle. So because we assume the radius of inner circle is A, therefore the surface area of a circle is pi a square. Therefore it is J into pi a square. We know that therefore current I is equal to J into pi a square, and the current density J is equal to I by pi a square into Az. Next, Therefore, substitute the current density in this equation. So if we substitute current density in the above equation, therefore the current enclosed equal to surface integral J into ds, so which is equal to I by pi a square. In place of J, I am substituting I by pi a square. I by pi a square integral, because it is a surface integral, we need to substitute two limits, phi limit and rho limit. So phi is equal to 0 to 2 pi. Rho limits are rho is equal to 0 to rho. Because the ambient path radius is rho, we need to assume from 0 to rho. So therefore it is rho into d phi into d rho. So here in place of ds, actually it is in place of ds, because in place of surface, because it is a surface integral, in place of ds, here we can substitute rho into d phi into d rho into az, where again az is a unit vector. In place of ds, we can substitute rho into d phi into d rho. Therefore, if we simplify the equation, here rho, we can integrate the phi separately and rho separately. If we integrate phi, so it is 1 into phi, 1 into d phi. 1 into d phi means it is phi only. If we substitute the limits 0 to 2 pi, we have 2 pi. Then if we integrate the rho, it is integration of rho is rho square by 2 between the limits 0 to rho. Therefore, it is I enclosed becomes I into rho square by a square. I into rho square by a square. Now we can find out the magnetic field intensity. So here I enclosed equal to, already we know that the magnetic field intensity of the line integral of magnetic field intensity into dl. So which is equal to h phi, which is nothing but h phi. The total becomes, because here it is h phi is a constant one, we can keep outside, h phi into a line integral 1 into dl. So there 1 into dl, line integral of 1 into dl means it is the circumference of a circle. So here the circumference of a circle is 2 pi r. We know that the circumference of a circle is 2 pi r. But here the radius of ambient path is rho. Therefore the circumference becomes 2 pi rho. The circumference becomes the 2 pi rho. Therefore the current enclosed I enclosed equal to magnetic field intensity hf into 2 pi rho. Now we need to equate the two equations, I enclosed and magnetic field intensity. So if we equate the two equations, h phi into 2 pi rho is equal to, it is I rho square by a square. And just you cancel the terms. Therefore the magnetic field intensity for the first circle is hf equal to, it is I into rho by 2 pi a square. Then we'll consider the second case. The second case is a less than or equal to a rho, less than or equal to b. Apply Amperes circuit law to the second circle or second path L2. So here if you apply Amperes circuit law to the second path, so it is a line integral of L2, h into dl is equal to I enclosed. According to Amperes circuit law, I enclosed equal to a line integral of h into dl, which is nothing but the current I, because we apply a current of I to the to the Ampere first circle. There are two conductors now. For first conductor we have applied a current I. For second conductor we have applied a current minus I. So because it is inner conductor which is having the current I, you can assume I enclosed equal to I. So already we have just calculated the line integral of h into dl is equal to, it is h phi into 2 pi rho, or just like it is h phi into integral line integral 1 into dl. Again the circumference of the circle is 2 pi rho. Therefore h phi into 2 pi rho, which is equal to I. Therefore the magnetic field intensity h phi is equal to I by 2 pi rho. It is simple to find out the magnetic field intensity directly, because we have applied a current of I to the inner conductor. Now we'll find out the magnetic field intensity for the third loop. Here the limits are b less than or equal to rho less than or equal to b plus t. So here apply Amperes circuit law to the loop 3. So here if you apply Amperes circuit law to the loop 3, so it is according to Amperes circuit law, a line integral of h into dl is equal to I enclosed. Already we know that line integral of h into dl, which is equal to h phi into 2 pi rho. H phi into 2 pi rho is equal to I enclosed. So here we need to find out the I enclosed to the total third loop. So here I enclosed equal to I plus some current density J into ds, because it is having the some thickness B plus T. It is having some thickness B plus T. Here we need to assume the I enclosed equal to I plus integral of surface integral of J into ds, where J is the current density. So here we can find out the current density directly. So here already we know that in previous expression, the current density is equal to, we know that from previous expression, the current density J is equal to I by pi a square. J is equal to I by pi a square. The current density J is equal to, we know that I by pi a square. So because here we are applying a negative current or minus I to the second conductor. So here I am assuming minus I. So by using this expression, directly I am writing the expression for current density for the second conductor. So here I am applying a negative current I. Therefore it is minus I by pi into a square, where a is the radius of a first conductor. Because we are applying the same expression to the second conductor. So here the thickness, we need to consider the radius is equal to B plus T. B plus T is the thickness of a second conductor, and B is the radius of second conductor. So between that we are applying the third loop, or between that we are applying the Amperes circuit law to the third loop. Therefore we need to consider the thickness and actual radius of the second conductor. For it is B plus T is the thickness minus B square into AZ. So simply by assuming the thickness and actual radius, we can directly substitute into the expression. Therefore the current density J is equal to, we have minus I by pi into B plus T whole square minus B square. Therefore current enclosed I is equal to I minus I by pi into B plus T whole square minus B square. Integral phi is equal to 0 to 2 pi, and integral phi is equal to integral rho is equal to B to rho, B to rho, rho into d rho d phi. We need to integrate this separately. And here we can simplify the expression. And here I enclosed equal to I minus I by pi into B plus T whole square minus B square into, if we integrate phi, we have 2 pi. And if we integrate rho, we have rho square by 2 between the limits rho to B. And here we can simplify the equation as I minus, so here it is B plus T whole square is B square plus T square plus 2AB minus B square. Minus cancel each other. We have T square plus 2AB into, here if we substitute the limits, we have rho square minus B square. Rho square minus B square by 2 cancel each other. Pi by cancel each other. So after cancelling the terms, we have I enclosed equal to, if we take I common, I into 1 minus rho square minus B square by T square plus 2TB. T square plus 2TB. And if you find out the magnetic field intensity, if you find out the magnetic, or if you substitute the I enclosed in that equation, therefore the magnetic field intensity H phi is equal to I by 2 pi rho into 1 minus rho square minus B square by T square plus 2TB. So which is the expression for loop 3. Now we need to apply the Amperes circuit law for the fourth loop. So where the limits are rho greater than or equal to B plus T. If you apply Amperes circuit law to the fourth loop, because the fourth loop is completely outside the conductor. So because it is completely outside the conductor, directly we can write that. So here the magnetic field intensity of the line integral of magnetic field intensity into dl is equal to I minus I, total currents, where I is the first one is the current of inner conductor minus I is the current of inner conductor. So if you add the total current, so I minus I equal to 0, because already it is outside conductor. Outside conductor means current is 0. When current is 0, automatically the magnetic field intensity H is equal to 0. So which is the expression for the fourth loop. So like this we can find out the magnetic field intensity of a coaxial transmission line. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.